Emanuele Latini from the University of Bologna. So before starting and diving deep inside the seminar itself, let me present you some kind of motivation about the things that we are going to discuss today. So, as you may have noticed, the talk is called Braided Differential Calculi and Cartan Geometry, noncommutative Cartan Geometry. So basically, we are attempting to try to describe the easiest model that you can think about coming from Cartan geometry, namely the affine case, using tools coming from noncommutative geometry. So basically, when you do Cartan geometry, you start with something that locally looks like a homogeneous space. Okay, so the idea is that you have a manifold that locally is like G mod H, where G is a Lie group and H is a Lib subgroup. In this particular setting, we are taking a look to the case where we are considering a semi-direct product. We are taking a Lie subgroup, and we have a homogeneous space on the other end. So we don't look. And on the other end, we are guessing on what kind of ingredient we can consider in order to replicate a similar kind of construction, starting with non-commutative Hopf algebraic objects. So our semi-direct product will be the Radford-Majid byproduct, or bosonization, stuff that you know very well, because it's here in my back. On the other hand, our Lie subgroup will be a Hopf algebra in the category of vector spaces. And our homogeneous space will be a braided Hopf algebra in a particular category that I'm going to introduce very soon. So a distinct feature of Cartan geometry is a Cartan connection. This is what I mean here with more Cartan, and you will see why. And rather striking phenomenon that happens to be true in the case of Cartan geometries is that usually your Cartan connection is separated into two different components. You have a principal connection, and you have something different that is called a soldering form. So how do we get this kind of description that we have here in the middle, starting from the ingredients that we have here on the left? We use the notion of a smash product calculus that I'm going to summarize very shortly. Okay, so let's start. Klein. Yes. I mean, on the left, you have Majid, Kohn, and Voronovich, right? Cartan by its own would be quite alone. So I thought, I mean, they look like lovers in this way. Okay. So let's start. My talk is divided in 4 sections. The first section is basically a very, very condensed version of Giovanni talk. I'm going to talk pretty much about the same things, and I will do it very fast, thanks to Giovanni indeed. Then I will start to talk about braided differential calculi, fundamental tool that we need in order to understand how this smash product calculus looks like. Then I will explain a little bit how this smash product calculus indeed works at the level of the Radford-Majid byproduct. And then finally, we also give some hints of non-commutative Cartan geometries in this affine setting that it's again, we consider a monoidal category. By MacLane coherence theorem, we can forget about the associators, because we know that this is always monoidal equivalent to a strict monoidal category. In particular, we will be considering braided monoidal category, that is a monoidal category together with a natural isomorphism, that is a braiding. These are, again, the explicit components that you have. We will always use this notation. And this braiding has to satisfy the hexagon relations. I mean, if you forget about this, you can look at the right side of the blackboard. Then, a fundamental example that we will start to understand is again the one of Jeter-Drinfeld modules, in particular left-left Jeter-Drinfeld modules over a Hopf algebra. So we have a category where objects are triples, where V is a vector space, then we have an action, and then we have a coaction. And these things have to intertwine in such a way that this relation that you have here is satisfied. So basically, you first stack, you then coact, and this is the property that has to hold. And in particular, you also want morphism to be left H linear and left H collinear. Okay, this is how you make this category monoidal again. If you forget about it, it's on the blackboard again. The monoidal unit is the ground field endowed with the trivial H-action and coaction. And this category is braided with respect to the braiding that we have here. So again, braided algebras, we have a braided bialgebra in a braided monoidal category to be a 5-tuple. So we have B, space, then we have a multiplication, a unit, a co-multiplication, and a co-unit. So the first triple that you have here on the left is an algebra in M. The other one is a co-algebra, and you also want that the coproduct and the co-unit are algebra maps. So a braided bialgebra, this is why you call it bialgebra, because you have to tell it twice. It's called a braided algebra in the category M if there exists a morphism such that this diagram here commute inside M. Okay, so again, very briefly, let's summarize two important constructions that we will need in the following. So again, transmutations, we start, here, actually, I'm going to describe this in a slightly more general setting than the one that Giovanni was suggesting. So we start with a regular Hopf algebra in the category of vector spaces, and we consider also a quasi-triangular Hopf algebra. And we assume that there is at least a bialgebra map between H1 and H2. There is this theorem from Majid telling us that we have a Hopf algebra inside the monoidal category of left H1 modules that is defined by the same vector space. Then we have an H1 action that reads basically the same that Giovanni was telling before, but the difference is that now we also have explicitly the map F that I was writing here above. And algebra structure and co-unit are the same, and co-multiplication and attivot gets modified. So essentially, the case that Giovanni was presenting before is the one where you have that F is the identity itself. Okay, this is also known as the braided quantum group associated to a quasi-triangular Hopf algebra. Okay, then again, let's summarize briefly what Radford-Majid bosonization is telling us. So we have a Hopf algebra. We now consider a braided Hopf algebra in the category of left-left Jeter-Drinfeld modules. We have a theorem from Radford and Majid telling us that this vector space has a Hopf algebra structure. Okay, this is very explicitly given by the assignations that you have here. And some more words that we can say is that the inclusion that you have here of the braided Hopf algebra B inside the smash product Hopf algebra B smash H is a trivial Hopf-Galois extension. Okay, so it's a very, very easy going case of a quantum principal bundle. In particular, the subalgebra of coinvariant elements inside B smash H with respect to the right H2 action is precisely B itself. Okay, when you have a trivial or more in general a cleft extension, you also have a notion of a cleaving map. It's not very, very relevant for the talk, but this is how the cleaving map looks like in this case. Okay, so let's move to braided differential calculi. Of course, if you have any questions, just feel free to stop me at any time. Okay, so we discussed first order differential calculi in monoidal categories. So we consider B to be an algebra in a monoidal category of choice. A first order differential calculus over B is a triple omega 1 B D consisting of a B bimodule omega 1 B inside C, a derivation from B to omega 1 B living inside the category C, and moreover a surjectivity condition. So namely we want that omega 1 B is generated as a left or equivalently right B module by the elements of the form DB. So this is basically very, very similar, almost verbatim, to the usual definition that you have of a first order differential calculus in the category of vector spaces. A morphism, on the other hand, is just a commutative diagram of this form. Namely, if we have two different differential calculi over the same braided algebra B, we just wanted this diagram to commute. Namely, the requirement that we ask is that the map phi intertwines the differentials that we have on the two calculi. So we denote the category of first order differential calculi over a braided algebra B, C diff B, very explicitly. So we have a universal calculus in this category. Namely, we have an initial object. So let B again be an algebra in C. Consider omega 1 UB defined as the kernel of the multiplication, and define a differential given in this way. Then we have that omega 1 UB du is initial inside the C diff B. So very, very shortly, the proof of this thing is very, very easy. So for any differential calculus inside the same category, one shows that there exists a unique surjective morphism on this way. And in particular, we see that every object inside the category can be obtained as a quotient of the universal by the kernel of this projection map. So this is why we call this object the universal first-order differential calculus on B. Yes, go ahead. Yeah, so this is the one that you have here. So you start with a braided monoidal, with a monoidal category in general. You take an algebra inside the monoidal category, and this is the category of differential calculi over the algebra B inside the category C. Okay. So I mean, the only requirement that you ask in principle is to take an object in the category. You want the differential also to be compatible with the category itself, and also the morphisms. This is a very, very easygoing generalization of the usual notion. Okay, so
Sorry, can I ask a quick question?
of
So
course.
you take the kernel of mu. Does
Mhm.
this always work? Like
No,
categorically?
indeed. Thanks a lot for yes. I I forgot to tell you that we would at least start by asking our category to be abelian.
Oh, okay,
Yeah,
thank you.
You need to be able to speak about kernels and co-kernels. Yes, indeed. Thanks a lot for the question. This is very important. Okay, so where were we? Okay, so we have this universal first-order differential calculus on B. Now let's talk about first-order braided differential calculi. Okay, so I mean here the additional requirement that I'm asking is not just to start with an algebra inside the monoidal category, but to start with a bialgebra inside a braided monoidal category. So we have a first-order braided differential calculus on B underlying. Just to fix some notation, usually when you read B underline, I'm talking about a braided bialgebra, at least. Usually it's a braided bialgebra or a braided of algebra. But I will say this quite a lot of times. So, okay, so a first-order differential calculus on B underlying is an object, omega 1 BD, inside the category that I was introducing before, such that omega 1b is left, right, or B covariant as a B bimodule, and moreover, the differential is left, right, or B collinear. Okay, so basically we are asking for the usual notion of covariance of a differential calculus with the additional requirement of satisfying the inner properties that we have inside the category. We can actually even talk about the notion of H covariance in the same setting. So if we start with a left H comodule algebra for a coalgebra H living inside the same category M, then we say that omega 1b is H covariant if it is an H covariant B bimodule and D is H collinear. Okay, in these cases, we can actually talk about the subspace of left B coinvariant elements of a first-order braided differential calculus, and the definition is the usual one according to the general picture that we have for the category of vector spaces. So those are namely the elements that are invariant under the coaction that we have on our differential calculus. Okay, so we denote the category of first-order braided differential calculi, on B by basically the same kind of notation. The only difference here will be that now M is a braided monoidal category and B is a braided bialgebra at least. And we also have the full subcategory of left H covariant first-order braided differential calculi that I will denote in this way. Okay. So we were showing before that if we start with an algebra inside the monoidal category and we consider differential calculi, on this, we can form a category, and in particular, this category admits an initial object. Here, in the context where, on the other hand, we start with a braided bialgebra in a braided monoidal category, we have somehow the same kind of behavior. So, start with a braided bialgebra in a braided monoidal category, then the universal differential calculus that is defined precisely in the same way that I was telling before. So we have the kernel of the multiplication and the differential consists precisely of the same assignment, is an initial object in the category of first-order braided differential calculi. So explicitly, we can keep the kernel of the multiplication with left and right b coactions that extend the co-multiplication at the level of the algebra. And very explicitly, this is what you get. Okay, so recall that these are the indexes referring to the braiding. And so for those of you who know about how usually you build up a coaction at the level of the universal calculus, you see that this is precisely what you should think about at the level of the category of vector spaces, but taking the usual flip and modifying it to be the braiding inside the category. So the well-definedness on the kernel of the multiplication of this coaction follows by the commutativity of this diagram that you have here. Then the coassociativity is verified using the hexagon relations that you have for any braided monoidal category. And then the proof goes as follows. I mean, you show that this is a left-left Hopf module inside M, and the initiality is precisely the same that you have in the standard non-braided case. Okay, now we know that this category has an initial object. How do we talk about covariant differential calculi when we have braided by algebra and we don't consider necessarily the universal differential calculus? I mean, the coaction is going to descend to the quotient explicitly by the commutativity of this diagram. Okay, so in particular, we consider the usual surjection that you have from omega 1 ub to omega 1b, and you define a coaction at the level of any covariant differential calculus over braided by algebra by the commutativity of this diagram. So explicitly, for any generator, this is how your coaction looks like. And again, this is very, very much similar to what you get starting from the classical picture in the category of vector spaces, where instead of having the flip, you have the braiding. So an entirely analogous construction gives us the right B coaction, and yeah, the proof is precisely the same. And yes, so now we know that the projection pi is a morphism inside the category MDiff and in particular, every first-order differential calculus on B can be obtained as the quotient of the universal one. Okay, any questions? Something? Is it all clear? Hope so. So let's go again on. We want to characterize a little bit the universal first-order differential calculus on a braided Hopf algebra. Let's see what happens. So if we consider a Hopf algebra B in the category of vector space and we fix B plus to be the kernel of the counit, then we can construct very explicitly a bicovariant first-order differential calculus on this tensor product, okay, with this very explicit form for the differential that is basically given in terms of the coproduct. Furthermore, we also have an isomorphism of bicovariant first-order differential calculi, okay? So basically, instead of thinking about the universal differential calculus in terms of the kernel of the multiplication, we can think about it as the object B tensor B plus, and in particular, how do you move forward between the two representations is together with this map that you have here. Okay, do we have something similar at the level of first-order braided differential calculi over a braided Hopf algebra in this case? The answer is yes. So we take a braided Hopf algebra in a braided monoidal category. The pair B tensor B plus D is a first-order braided differential calculus on B, where very explicitly we have the left B action, right B action, and left coaction given almost precisely as in the classical case of vector spaces. And moreover, we have something a little bit different at the level of the right B coaction. That is the last formula that you can see displayed here, that I'm going to comment about very shortly now. Moreover, we also have that the map chi that we have above, it's an isomorphism inside the category of first-order braided differential calculi over a Hopf algebra. So let's see how this right coaction works, because surely so basically, if you take a look to the left B action and right B action, one is the left multiplication, the other one is the diagonal, but you have to, yeah, you have to take the flip. The left big coaction, you are just taking the coproduct on the first component. And yeah, the right one is the one where things are going to get a little bit more complicated. But if you recall how the right coaction looks classically, then this is basically the only thing that you can do. I mean, but I remember that actually we already talked about this once at the blackboard. But yes, no, I mean, it's very, very similar to what you have classically. The only difference is that instead of the flip, you have the braiding. But to prove that this is indeed the correct thing to have, it's not, I mean, yeah. Yep, precisely. Yeah, this is for a Hopf-algebra in vector spaces. And indeed, if you see there, you have the lower indexes. And whenever we have the upper indexes, as in the notation of Giovanni, we are talking about braided stuff. Precisely. Somehow, yes, this is what happens. Okay, so let's see a little bit how this right coaction works. So as I was saying, the bimodule and left comodule structure are very, very easily understood. The braiding enters into play, but on a minor side, let's say. So to the right bicomodule structure, we have to use the naturality of the braiding. Okay, and in particular, we have to also to use the fact that the coproduct is a morphism inside the category. And this gives us this very enlightening condition, I mean, technical things that you need in order to prove that this thing is well defined. Then after this, you can verify that chi is right B collinear, or to say that intertwines these two maps that you have here, so this delta B and delta B tensor B plus. And then it follows that delta B plus is a coaction from the fact that delta B is a coaction at the level of the universal calculus, and now chi is a linear isomorphism. Okay, so now let's talk about the quantum Morer-Cartan form. So if you remember the first nice picture that we saw, this thing is going to be quite central to what is going to come afterwards. So we start with a Hopf-algebra, a braided Hopf-algebra in a braided monadal category, and we consider a first order differential calculus on it. In particular here, it's enough to consider a left covariant first order differential calculus, okay? So the quantum Morer-Cartan form is this map that you have here, this assignment. And why do we like this map? Because of many reasons. In particular, this map is surjective, is right bilinear morphism inside the braided monadal category M, and in particular, the right B-module structure at the level of the coinvariant one forms is given by the braided right adjoint action. Okay? So, I mean, very, very easily one can verify that the coinvariants hold, and this is precisely what you do even in the classical case. The only difference, again, is that you have some braiding indexes that are not very, very crucial here because you are going to recover quite quickly a co-unit here, and this shows that your form is coinvariant. Then surjectivity and right bilinearity follow exploiting the properties of the antipode isomorphism in the category. Okay, why are we interested in this Morer-Cartan form? So as I was saying, this will be quite crucial for the part where we are going to discuss something that is akin to noncommutative Cartan geometry, but even before that, this is very, very useful to start to talk about some kind of classification theorem for braided differential calculi, as it happens for the classical case of vector spaces. So in particular, it turns out that first-order calculi on braided Hopf-algebras are classified. So in particular, we have a braided analog of Voronovich classification theorem. And yes, the role of the braiding is the one that forces us to replace module structure, in particular bimodule structure, and also the covariant structures. And in particular, we need to change the role of the ordinary adjoint coaction by the braided adjoint coaction in this case that I'm going to define now. So the braided right adjoint coaction on B on itself is the map that you see here. Then we have that a right ideal inside the B underline plus is called the coinvariant, co-ADR invariant in particular, if the condition that we have here holds. It's basically a co-ideal under this coaction. So the theorem that I'm going to present now will establish a bijection between left first-order braided covariant differential calculi on the braided of algebra B and right ideals inside the kernel of the co-unit of the same algebra. And in particular, we also can say something more. So first order braided differential calculi, so namely the ones that classically should correspond to bicovariant differential calculi, are also such that the classifying ideal is invariant under the right adjoint coaction in the braided setting. Okay, so this is the datum of what I'm going to discuss now. So we consider a Hopf algebra in a braided monoidal category. We consider a right ideal inside the kernel of the counit. And we consider this space here. And in particular, we endow this space with the following bimodule structure. Okay, so on the left, basically, we have just the left multiplication on the first factor. On the right, we basically have a diagonal kind of action on the tensor product. And we can explicitly define a differential in this way, where pi is the canonical projection map to the quotient. In particular, we can also define something that it's going to be a left coaction at the level of this bimodule, that now we will see it's actually a differential calculus. In particular, omega 1b di is a left first-order braided differential calculus on B, and moreover, if the classifying ideal inside B plus is closed under the braided right adjoint coaction, then we also have a first-order braided differential calculus where the right coaction is the one that you can see here. So, on the other hand, every first-order braided differential calculus on a braided Hopf algebra B arises in the same fashion. Okay, so morally speaking, we have the correspondence that I'm outlining here below. So you start with a left covariant first-order differential calculus on B. And what is the classifying ideal? Is the kernel of the Maurer-Cartan form, the map that we introduced in the slide before. On the other hand, you start with a right ideal inside the kernel of the counit. How do you get a differential calculus? You get a differential calculus by assigning this space together with the bimodule structure and differential and coaction that I was outlining here above. Okay, so let's move to an example, a very explicit and very beautiful example that is again the Swidler-Hopf algebra of which Giovanni was talking about before. So we take this four-dimensional algebra. Coproduct and counit are those that you can see here, but now you know this very well. We can consider a first-order differential calculus on this Hopf algebra. Okay, so we have this student left-H covariant first-order differential calculus where on the generators as following, and then you can linearly extend at the level of the whole algebra. Unfortunately, this calculus is not right H covariant, and in particular this happens because the classifying ideal does not close under the right adjoint H action. Okay, so we have this Swidler-Hopf algebra. We already know that this is we can construct the corresponding transmutation in its own category, in its own braided monoidal category of left modules. So let's do this. For lambda, an arbitrary parameter, H is a quasi-triangular Hopf algebra where the R matrix, the R matrices, if you want, are classified and all look like this. In particular, we consider lambda equal to 0 for simplicity. And we consider the transmutation of H into its own braided monoidal category of modules again. So explicitly, this is what you get. As Giovanni was saying before, basically you are getting that one generator is going to become primitive under the coproduct, the other one is going to stay group-like, and you also have these two actions outlined here above. So the braiding again is induced by the R matrix, and very explicitly this is how it reads on the generator. This is not going to be crucial, but let's see what happens at the level of the differential calculi. So we consider a first-order differential calculus in the category of left H modules on H underline, given by the H bimodule span of the same generators that we have as before. Because, I mean, recall the fact that when you're taking the transmutation, the linear space that underlies your new braided Hopf algebra is going to be the same. So we still have, again, a two-dimensional differential calculus. So this is left H braided, again. But what we also find, and that we find also very beautiful, is that it's also right H braided. So you get an extra symmetry while moving from the realm of differential calculi over a vector space, over an algebra in the category of vector space, to a differential calculus in a braided monoidal category over a braided Hopf algebra. So in particular, this is how the correction looks like. And in particular, you can understand how the kernel of the Maurer-Cartan form looks like, and this is just given by the span of this element here, and you can actually show that this consists precisely just of this element. And you can actually see very easily that when you calculate the braided right adjoint coaction on the declassifying ideal of the calculus, you're getting something that is closed as a co-ideal. And so in particular, you get a bicovariant first order differential calculus on the transmutation. This is a very, very nice example. If you want, this thing of transmutations is a very, very explicit way to produce braided differential calculi, starting from something that is just a quasi-triangular Hopf algebra, and the datum of a first-order differential calculus over this quasi-triangular Hopf algebra. Okay, I would actually like to comment a little bit more on this, but for...
Can I ask a question?
Absolutely, yes.
I think I missed the point. What's the extra symmetry that you're saying is coming in?
Yes, so the calculus that you had before, it's not right covariant. Oh, sorry, we have to go even before, yes. So this is a left covariant first order differential calculus, okay?
We've got Sweetler's Hopf algebra. You've got a first order differential calculus in the category of vector spaces.
Yep.
And now you're saying that this is just left covariant and it's not right covariant.
Yes,
it's not a bicovariant calculus.
You can verify this in multiple ways. You can just try to calculate the correction by brute force and it doesn't work. Otherwise, you just see that the ideal is not closed under the right adjoint correction.
As usual, yeah.
Now you take the transmutation. And in particular, I mean, you can do this in many different ways. In particular, you can transmute by the identity.
What are you transmuting with? You need a module. What's the module that you're...
So you know that the Sweetler's Hopf algebra is a quasi-triangular Hopf algebra. So in particular, the category of modules is braided. Okay, so you can transmute the Sweetler's Hopf algebra inside its own category of modules.
Okay, sure.
So I think that this is what's written here. No, don't worry about it. And you can do this by the identity indeed, or you can take any bi-algebra map that you like into the Sweetler's Hopf algebra, if you know some about it. You're actually not even forced to choose the identity to be your bi-algebra map. You can take the endomorphism of the bi-algebra endomorphisms of your Sweetler's Hopf algebra, and you can try to generate a new transmutation, basically.
Okay. And then by looking then at this braided Hopf algebra, this transmuted Hopf algebra, and the transmutation of the calculus, then you get something that has an extra.
Yeah, so to be precise, this construction that we are outlining here, it's not a transmutation of the calculus, okay? So this is not transmuting a calculus. So we are transmuting the algebra and we are constructing a first order differential calculus in the same fashion as we constructed a first order differential calculus at the level of the non-transmuted algebra. Okay? There is actually a way in which you can transmute a differential calculus, and in fact, I forgot to include some slides about it, but maybe it's better because otherwise it would have been too much time, but we can talk about it afterwards. Yeah, for example, if you start with a bicovariant differential calculus, you can always take the transmutation. Yeah, and this is still going to be bicovariant. It's nice. It's very symmetric if you start with a bicovariant. Otherwise, if you start with something that is only left or right covariant, as you prefer, it can happen that you get something that is bicovariant. And this is why we were interested in trying to do something similar at the level of UQ SL2, right? Because you can actually think, what does it happen if we try to take something that is just left covariant as a differential calculus on SL2, but their matrix is horrible. So, okay.
Because commenting very briefly, if I may, so the calculus stays the same, right? So it's the same vector space. It's just viewed as in a different way as a total model. That's what's changing.
Yeah. It's precisely the same differential calculus, if you want. This is why I was saying that we are mimicking the construction of the other differential calculus. It's not like we are modifying it by using the transmutation. We are starting with the same kind of assignation, verifying that it is a differential calculus, and then trying to see which kind of symmetry properties it holds. Yeah. So, and I mean, very quickly, this is what we did at the level of the Swidler's Hopf algebra seen as a quasi-triangular Hopf algebra. We also did this and with the dual co-quasi-triangular Hopf algebra, and the thing stays the same. Yeah, so it's also very symmetric on this front. Okay, so let's move to differential calculus on Radford-Majid byproducts. I think that I have to start to go a little bit faster. So we fix a Hopf algebra, and we of Jeter-Drinfeld modules of the original Hopf algebra, and we also assume our antipodes to be bijective. So we consider the Radford-Majid byproduct between the two objects. And we know that we can undo this tensor product with the structure of an Hopf algebra. Then, given a first-order differential calculus on H and a first-order differential calculus on B in the category of Jeter-Drinfeld modules of H, the question that we ask is, can we construct a compatible first-order differential calculus on the smash product, given this data? And the answer is yes. And this is known as the smash product calculus. And in particular, this provides a construction such that we have a differential structure on, no, okay, I said it. A sometimes will be B smash H. So this differential structure with which we endow B smash H actually sees simultaneously the differential structure that we have at the level of B and the differential structure that we have at the level of H. And in particular, this can also be presented in a slightly more general setting. I mean, here I'm starting with a braided Hopf algebra and a Jeter-Drinfeld modules, but we have this theorem that tells us that it is enough to consider a first-order differential calculus in the category of left H modules on a left H module algebra B, and also a left covariant first-order differential calculus on H. And then we automatically get that this K module is actually a B smash H bimodule. In particular, those are the bimodule structure. They are not very enlightening, so don't care too much about it. But this is how you give this a bimodule structure. And in particular, this object here is a first-order differential calculus on B smash H, where the differential is explicitly given in terms of the differential on B and the differential on H. Okay, in particular, if you start with a bicovariant differential calculus at the level of the Hopf algebra, you can actually see for free that the smash product calculus is going to become right H covariant with respect to the coaction that we have here. Okay, so if you have some question about the indexes and so on, feel free to stop me. So those are the indexes of the right H coaction that we have at the level of the differential forms on H. This is just the standard coproduct that you take on H. Upper indexes, again, are going to refer, on the other hand, to the braided indexes coming from the braided Hopf algebra structure that we have on B. So, covariance of the smash product calculus. So, if we ask B underline and omega 1B to be object inside the category of Jeter-Drinfeld modules, we get an extra symmetry to this smash product calculus under further minimal assumptions. So let's see what happens. We take a bicovariant first-order differential calculus on H. We take a left braided first-order differential calculus on the braided Hopf algebra B in the category of Jeter-Drinfeld modules of H. Then what we get is that the smash product calculus is left B smash H covariant, and this is how the coaction is explicitly given. Again, the formula is very technical, but don't bother too much about it. And in particular, this assignment that we have here denotes the braided left B coaction at the level of omega 1B. Okay, so it's enough to consider just left braided first-order differential calculi for this matter. So, from now on, if I fail to recall due, usually the assumptions with which we will be working are a bicovariant we proved that starting with these assumptions, we are actually guaranteed that our smash product calculus is going to be left covariant. What about bicovariance? Let's see. We define the vertical map associated to the smash product calculus in this way. That's a very weird map. We have a map that starts from omega 1b at length inside omega 1h tensor b. And we will use this square brackets notation to denote how the vertical maps look like. In the end, if you think about it, it's not so complicated if you are familiar a little bit with differential calculi on Hopf algebras. And we have this proposition telling us that if we start with a bicovariant differential calculus on H and a braided bicovariant first-order differential calculus on B, the following notions are equivalent. We have a bicovariant first-order differential calculus on the Radford-Majid bosonization. The vertical map is well defined, and this is how the coaction looks explicitly, very beautiful. And in particular, this is what I found to be the most enlightening condition. B direct sum with omega 1b is a braided graded Hopf algebra in the category of Jeter-Drinfeld modules of the direct sum of H with omega 1h. Okay, so to clarify a little bit what is happening here, there is a bijective correspondence between graded Hopf algebras and the bicovariant differential calculi of Hopf algebras. So in particular, this direct sum here is a Hopf algebra with suitable coproduct, antipode, and counit. Okay? The same on this other end, but this is now going to become a braided graded Hopf algebra. When you have this condition to be satisfied, your differential calculus is going to be bicovariant. Essentially, I mean, maybe I will comment a little bit afterwards about this. Let me move forward. And if you have any question, of course, just interrupt me. But let's talk a little bit about the quantum Moore Cartan form, because this is very interesting. So the smash product calculus on B smash H is defined in terms of the calculi on B and H. By the fundamental theorem of Hopf modules, we know that every first-order differential calculus that is covariant can be realized as a tensor product of the algebra and the coinvariant forms of the calculus. So a question that we ask is whether or not the coinvariant one forms are going to reflect the split structure of the smash product calculus. And instead of thinking directly to the covariant one forms, let's think about the Moore Cartan form, because we know that this is a surjective map into the covariant elements. We have the following lemma telling us that if we start with a left B smash H covariant calculus on B smash H, and if we consider the quantum Moore Cartan form of this construction, then this following formula holds. Again, this is not very enlightening, but let me comment a little bit about it. So what this formula is telling us is that if we start with an element that lies inside the kernel of the counit on B smash H, we are going to have essentially two components that are direct summands. One component is essentially the coinvariant forms at the level of the Hopf algebra H. The other component is a little bit more mystic to say. In particular, we have that the last term is going to give us exactly the coinvariance on H. And how do we understand this other term in blue on the left? We are actually going to realize a very direct isomorphism with the coinvariant forms that we have at the level of the differential calculus on B. So this proposition is telling us that indeed we have this isomorphism at the level of vector spaces that is explicitly given by this assignment that you can read here. So the proof of this statement fundamentally follows from the fundamental theorem of Hopf modules together with the exactness of this sequence and faithfully flatness. So this sequence is exact for any smash product calculi that you have automatically. It's even split exact actually. And the faithfully flatness holds because, as I was saying in the beginning, B included inside B smash H is going to give us a trivial Hopf-Galois extension, and so in particular, faithfully flatness holds by default. So a question that we ask is that do we have actually something more? Do we have some more structure on this map, or is it only an isomorphism of vector spaces? This map is actually a morphism inside the category of right H modules. And in particular, both the restrictions at the level of B plus smash H and 1 smash H plus are. So maybe let me go a little bit. So here we have this element B smash H plus that gets sent into these two different components. Actually, one can see that these terms here comes from the restriction of the Morer-Cartan to the elements of the form B plus smash H. And this other term here comes from the restriction of the Morer-Cartan at the level of 1 smash H plus. And this space here is actually isomorphic to the two spaces that I was telling to you now. So this is actually B plus smash H plus 1 smash H plus. Okay, so again, the Morer-Cartan restricts to these two spaces as a morphism inside this category. The restriction to B plus smash H is a morphism in this category considering the relative right adjoint H coaction. Okay, so this is just induced by the regular adjoint B smash H coaction, but you have to project. Okay, so you are going to have some kernel of the counit on B appearing to this factor, and this is the explicit formula that you get. To see what the comodular structure with which we can endow the coinvariant forms are. This is going to be very crucial in a moment. So we can consider this space of coinvariant elements. Okay, this is one of the two direct summands that you had before in the coinvariant elements as mapped from the quantum Morer-Cartan form. And we can actually give a structure of a right H covariant H module with these two actions and coaction, as you can see here. One is basically an adjoint kind of action, and this is basically the coproduct at the level of H. And we can actually also see that lambda 1b is an object inside the category of right-right Jeter-Drinfeld modules with this structure. So just to comment a little bit about these last formulas that we have here, those are basically the action and coactions that you have according to the equivalence of categories between left Jeter-Drinfeld modules and right Jeter-Drinfeld modules. So basically you have a Jeter-Drinfeld modules on the left. This is how you explicitly make this to look also as a right Jeter-Drinfeld module on the right. And why is this important? With all of the comodular structure that we outlined before, we have that the space of left coinvariant one form splits as a right H covariant H comodule into this direct sum that we have here. So in particular, we started with something that was a little bit hard to understand, right? The space that we have here. Now we actually see that this space is isomorphic in one of the best ways possible just to the coinvariant elements that you have at the level of the base space. Okay, to prove this, one uses the comodular structure of the previous lemma together with the definition of the isomorphism psi that we constructed before. And moreover, now given that the Morer-Cartan form was also proven to be a morphism of right H comodule and also in particular trivially of right H folds, we have a well-defined surjective morphism in the category of right H covariant right H module given as follows. If you want, you can think about the Morer-Cartan form as disassignation for the case of the smash product calculus. But nevertheless, this is the thing that we wanted since the beginning, to show that this splitting of the coinvariant elements work. Why? Because the form the classical splitting associated with a semi-direct product. Okay, so we are actually now also having another motivation to understand that smash product algebras constructed in this way are very, very much akin to the classical notion of semi-direct product. Okay, finally, okay, I'm still on time, wow. Let's move to the very, very last part about noncommutative Cartan geometries. So very briefly, let's outline how the things work at the level of the classical differential geometry. So we consider a principal G bundle. In particular, it is well known that the tangent bundle of the total space fits into this canonical short exact sequence. Okay, and in particular, this space VP is the one of the fundamental vector fields, and it's understood as follows. Oops. Okay. So a principal connection on P is a G equivalent splitting of this sequence. In other words, we have a form omega on P with values in G, with omega evaluated on the fundamental vector fields, giving us x for any x inside the Lie algebra G. And in particular, we also have this condition to hold for any element inside G. So now let's fix a reductive Klein geometry. In particular, let's assume that this is our splitting. And let's consider a principal bundle, a principal H bundle, PM. And in particular, let's also assume that the dimension of M is just the dimension of G mod H as a quotient. So a Cartan connection modeled on this homogeneous space is a form on P with values in G such that omega P is linear isomorphism at every point inside P. And this is going to satisfy the same equivariance and normalization conditions that you have for a principal connection on the H component. So this splitting decomposes our Cartan connection into a principal H connection omega and a soldering form. That is one form on P with values in M. Okay? That is this component of the splitting of our Lie algebra. So we have a proposition telling us that the soldering form theta is going to induce an isomorphism of vector bundles between this associated vector bundle and the tangent bundle over the base manifold M. And this isomorphism is known as the frame resolution of the tangent bundle. So now I'm going to argue that we have something that is very similar at the level of our model. So we have a surjective morphism in the category of right H covariant H module defined by this assignation. And the proof that this works is basically coming from the commutativity of this diagram. So in particular, this map chi is actually defined by this. Why are we interested in this map? Because now, since we know that chi is an isomorphism, we can actually understand how the restriction of the quantum memorial Cartan form at the level of B plus smash H is understood in terms of the Morer Cartan form at the level of P. But first, let's spend some word about the classifying ideal of the smash product calculus. So, very, very explicitly, we take any smash product calculus on a braided Hopf algebra, on the bosonization obtained by the smash product of a braided Hopf algebra in the Etter-Drinfeld modules of a Hopf algebra H. The classifying ideal of this smash product calculus is going to be very explicitly given in terms of the ideal that classifies the differential calculus on B and the ideal that classifies the differential calculus on H, precisely by the elements of this form. Now, since psi is an isomorphism inside the category of right H covariant H modules, we know that this ideal, that is going to be the kernel of the Morer Cartan form, indeed is going to be understood as the kernel of the composition of these two maps. And this is actually how you see that this ideal has to look like this. So, the two conditions inside this formula indeed arise because the preimage of IB under chi is a right B smash H ideal, and the component along H is actually very, very explicitly given because of the fact that you already know very well how the coinvariant forms at the level of H look like. Okay, so now that we know all of these ingredients, we can say that the Morer Cartan form on B smash H, that again here is just A, is going to decompose explicitly by the sum of these two components. Okay, so the component on H was very, very clear since the beginning. This other component at the level of B, now it's very much understood because of these two morphisms, chi and psi, that we constructed along the way. So, finally, and let me say that omega B, now, for us, gets the interpretation of a soldering form on the bundle. Finally, theorem, we have an isomorphism in the category of left B modules, given by this assignation. So we start with the balanced cotensor product over H, and we move inside the base forms. And the explicit inverse of this morphism is constructed in this way. So how does this morphism work? Why is this an isomorphism in this category? This follows basically because of the Takeuchi equivalence for the quantum homogeneous space B inside B smash H. And yes, in particular, this isomorphism, if you want, is going to be precisely the counit of the adjunction, and the inverse is going to be basically the Hopf-Galois map of the bundle. So, in particular, I mean, I already said this before, but why not? Let's say it again. This map, the Morer Cartan form on B, acquires the interpretation of a soldering form in the sense of Beck's Majid, and the datum S omega B consists of a quantum frame resolution of the bundle. Okay, so this is a diagram, I mean, in the attempt of clarifying a little bit what is happening here, so I will just steal you 1 minute more. At the level of vector spaces, we have the representation that you can see here above. You have a Hopf algebra H. You take the kernel of the counit. The cotangent space is going to be basically H plus modulo IH, where IH is a right ideal inside H plus. Okay? Then you can do actually the same kind of construction at the level of the braided Hopf algebra B. Okay? Now, how you understand everything at the level of your quantum noncommutative analog of the semi-direct product, you consider the kernel of the counit of V smash H, which is canonically isomorphic to this space. Then you can actually see, starting from this, that the coinvariant forms of your differential calculus are going to decompose in this way. And then you understand the coinvariant forms at the level of B plus smash H, so those that are in the image of B plus smash H, are actually understood just as the coinvariant forms at the level of B. Okay, so some references, and thanks for your attention. That's it.
All right. Questions for Antonio?
Maybe. So the examples that you're looking at so far, the Smash products and Sweetler.
Yes.
What about beyond this?
What would be beyond this?
Beyond, yeah.
Yeah, so the idea would be to consider sheaves, basically. I mean, it's just an idea. It's not like we are actually working on this actively.
Yeah.
But the natural idea is that since a Cartan geometry is modeled by an homogeneous space, right? So you have a manifold that locally looks like an homogeneous space. The idea would be to consider a classical topological space, where on each patch you get a trivial Galois extension of this way. And this is an idea. Another thing that we were thinking about looking to is the case in which instead of considering a trivial Galois extension, you consider a cleft extension. Okay, so these are cross product of algebras. So geometrically speaking, the difference is not going to be so evident because one is a trivial principal bundle and the other one, if I'm not wrong, is just a trivializable principal bundle. But nevertheless will be something interesting to look at least from an algebraic perspective. Whereas from the geometrical side, I guess that the approach with sheaves can be interesting, even though maybe very technical.
I guess, yeah. I guess really I'm going to the question that we already discussed in Quantum SU2.
Yeah.
And whether this can be done.
So, I mean, at the level of UQG, in my opinion, it's going to be hard because of the presentation of the R matrix. At the level of OQG, you actually have an R form, and you have a very explicit presentation.
And it's not bad at all.
No, but the point is that crazy calculations are going to come.
You can stick it into mathematics.
Yeah, that's true. That's true. You can try to write a computer program in order to see if this works. I'm very bad with computers.
I can.
Would you like to do it? Okay.
No. I meant I'm able to put the cocos triangular thing into Mathematica, which means it's not difficult.
Okay. No. But so together with Giovanni, we spent some afternoons in trying to understand whether or not this thing is going to work. In principle, there is no reason to see why it should or it shouldn't. So one has to do the explicit calculation and see what happens.
So what you would be doing is you're going to take the transmutation of quantum SU2 using the co-quasi-triangular structure.
The product is going to change.
And then you try to find a calculus.
Exactly. So basically, in the same way on which you started with a calculus on the Sweetler, and you tried to construct some braided analog at the level of the corresponding braided group.
And so first, how does it work, the classification you classify them in terms of ideals. What about, I guess that would be my next question. What about the tangent space classification? That's, I mean, because everything works so smoothly.
Yeah. No. I mean, you can do it with tangent spaces. But I mean, if you want to consider the tangent space of OQSL2, you are basically going back to UQSL2 now.
Yeah.
So this is why this is a thing that we also discussed together one afternoon, and
Sure, then the
because you know
transmutation-
how the condition is going to look like, it's very explicit if you know how your tangent space looks like, right?
Yeah.
So you basically have again to calculate some kind of a joint action in the elements and see if it closes nicely or not. But again, in that case, you have to transmute the coproduct, and the transmutation of you need the adjoint coaction. The adjoint coaction needs the coproduct, and the coproduct needs the R matrix, and the R matrix has this infinite dimensions.
If instead of, okay, this is turning into too long a discussion, but like instead of taking the transmutation of UQSL2, why don't you just look directly at the joule of the transmutated? I mean, does a hop, look, maybe this is turning into too long a discussion.
We can surely talk about it afterwards. Okay.
It's from the in-person audience.
So is the last picture you showed the same as the first picture that you showed? Like the 3 levels, you also had 3 levels in the...
Yes.
Yeah.
Yes. Basically, yes. This is now more explicit, right? Because now you know how the theory looked like. But this is the level of the semi-direct product. This is the level of the group, and this is the level of the homogeneous space.
Yeah.
Basically, yes.
Cool.
I mean, this is how first you get this, and then you draw the picture with the faces of Aronovich and so on. Yes.
Another more very elementary question. Can you go back to the definition of the calculus in a monoidal category?
Surely.
I'm just curious what happens to the Leibniz rule in this.
Oof, a lot of endow. Almost there. Okay, here we are. I mean, you're just asking for your object and your map to satisfy the compatibility condition that you have inside your category. I mean, this is actually also for the covariant part, but if you don't care about covariance, you can just forget about D being also being collinear. No, but the Leibniz rule, of course, has to hold. You are asking for it, yes. This has to be a derivation. No, not really. No, not really, because you are taking the AB plus ADB as the usual definition. Yeah, this is the same, yes. Yeah. I mean, you can take transmutations where you now look things from the perspective of having a co-quasi-triangular structure, and in that case, it's the algebra structure that gets modified. I mean, it's the Leibniz rule, it's the same, but it's the multiplication that is changing. So yes, in some sense, if you want, but no in another, yes.
Any questions from the online audience? Yep, Freddie, go ahead.
Yeah. Hi, Antonio. So I have hello. So I have a very basic question, maybe. So in your definition of first order braided differential calculi, so you have the definition of bicovariant. So if we ignore the word braided, so we have this condition about the right adjoint coaction, no?
Yeah, yes.
In your case, so you have something similar? I remember.
Yeah, it's here.
So the bicovariant condition is equivalent to the
So if you think about your favorite Voronozh classification theorem, this is the same. So the condition of being bicovariant as a differential calculus in a braided monadal category is the same as asking if the ideal that classifies the calculus is invariant under this braided right adjoint coaction.
Yeah, I see. But you have the antipode on the left, but it has to be on the right, or I don't, as far as I remember.
No, I think, is it on the right? Maybe it's on the right. Yeah, sorry, maybe, yeah, you're correct. It's B2 tensor B1 S of alpha B3, maybe. Yeah. I don't know what happened, but yeah, you're correct, I think.
Yeah, okay. That was my question.
Thanks a lot for the question.
Thank you.
Other questions from the online audience? Okay.
Yeah, this is
Ray's asking a question without the mic.
It's a question about the notation for the alpha. Where does this come from?
So this is from a very, very distinguished mathematician called Thomas Weber. And also Paolo Aschieri, if I'm not wrong. I mean, it's very, very convenient to carry out calculations.
So this is Weber notation.
Yeah.
I think Thomas, you should put brackets, no?
So in fact, you see that to make both of you happy, I'm using the square brackets on the Swidler's indexes, but not on the braided indexes.
So the question
it's
was
very, very
about
convenient to do.
So the question was with the alpha indices?
Yeah. I was telling that as far as I understood, it's you and Paolo that use this notation in the first place, right?
Yeah. So you might ask why is the index on the left side, right? So that's a bit strange. And so the reason is that you might think of an R matrix that is acting. So if you would write the braiding for an R matrix, this would be we have the R lower alpha acting on the first tensor R upper alpha acting on the second. So now here you don't have an R matrix, it's just a braiding. So since we are just used to work a lot with R matrices, we are using the same, just we drop the R, but we keep the alpha that is on the left side because things are acting from the left. That's where this came from. And I don't know if it's a good way to write this down, maybe not, but for me it's very helpful and computations are a bit easier.
I mean, for the first time that I used this notation, to me it looked very, very natural, I have to say. So
it's nice to see the hexagon identities in terms of this.
Yeah, indeed.
Right.
For example, if you take a look to this fake right adjoint coaction, naturality and the fact that S is a morphism in your category is going to tell you that this index that you have inside, you can actually take it outside and don't bother too much. It's the same. It's very, very convenient.
I think there are no other questions. We'll end it there and let us thank Antonio once again. And we have one more online seminar planned for next week, a double seminar.